So this is a review of Chapter 7. Only a couple chapters back, but I bet you've already forgotten what was in it. I forgot until I looked at the old test that we gave you. So in Chapter 7, we had to know how to do vertical asymptotes, horizontal asymptotes. X and Y intercepts are always pretty easy. Well, the x-intercept is where what? Y equals 0, and the y-intercept is where what? X equals 0. But when in the context of a rational function, let's say we've already got a factor, and it factors to this. Do you remember the whole, there's holes, there's vertical asymptotes, there's horizontal asymptotes. There's things that make this whole function equal 0, and then there's things that make this function crash. Okay, so in rational functions, which is the main theme here, you have to know the domain first of all. Domain is what can you feed this thing safely? Remember, if it turns into 0, that's okay. If it turns into something over 0, like 2 over 0, then you've got a problem. All right, would you try to figure out for me what the domain of this thing is? Any vertical asymptotes, horizontal asymptotes. I'd like you to figure out the y-intercept, the x-intercepts, and if there is a hole, exactly where is it? Not just like the hole is at x equals 2. Where exactly is the hole? 2 comma what? All right, I'm going to pause for a minute while you give those a shot. Okay, starting to hear some talking, so I'm assuming that means you are ready to go. So the domain on this thing. Domain is what can you feed it safely. I don't care if the top turns into 0 for the domain. That'll just make it equal 0. But if the bottom turns into 0, I'd have a problem. So it's all reals except x cannot be -2 and x cannot be -3. Could you have done this in number line format? Sure. Everything would be shaded except -2. And, oh, I should make that -3 and that -2. Like that. Any questions about the domain? Okay, the next one. The horizontal and the vertical asymptotes. Here's where they come from. These things lead you to the vertical asymptotes because these guys, the reason they don't work is they either make holes or they make vertical asymptotes. Which one makes the hole? That guy, because that cancels with that. And so the -3, that one's a hole, and this one is an asymptote, a vertical asymptote. Okay, so the vertical asymptote is at x equals -2. There's a dotted line at x equals -2. So if I was going to actually graph this thing, I'd go over here, there'd be a dotted line right there. Okay. Just missed it, but I was close. Okay, next. I just mentioned the hole. I may as well go down there and do it. If the hole is at x equals -3, then -3 is the start of the hole. But how do you get the rest of it? You take your resultant function, the thing that results after something cancels, and you say my new function is going to be x minus 3 over x plus 2. That will tell you the other part of the hole. Because if -3 is the x, you stick a -3 here, and I get -6 over -1, which makes +6. That's where the hole would have been. I hope you get that we're talking about something that doesn't exist. But if it were going to exist, it's an empty spot on the graph at -3, 6. Okay, the horizontal asymptotes are the ones that Bob will tell you. Bob will tell you all about them. Remember this deal? Bigger on bottom. If it's bigger on the bottom, then it's y equals whatever's on the outside. If it's a bigger on top, then it's y equals none because there are no bots. And same on both. If the degree is same on the top and the bottom, then those are an SOB to figure out. Same on both. So y equals a ratio of the lead coefficients coefficient. So y is a ratio if it's the same on both. This one was a same on both because the degree on the top is degree 2 at the beginning and degree 2 here also. But if after it's reduced, it's degree 1 and degree 1. The point is, either way, it's same on both. So if it's the same on both, we do a ratio of the lead coefficients. Since the lead coefficient here is a 1 and here is a 1, it's y equals 1 over 1, or y equals 1. Remember those? Okay, so horizontals, you got to remember those 3 rules. Bigger on bottom, bigger on top, same on both. Okay, next up, the y-intercept. The y-intercept is where x equals 0. You go stick in a 0 here and here and here and here, and I can even do it in this resultant function because 0 isn't going to crash my function. So I'm putting in a 0 here and here, and I get negative 3 over 2, and that means y is negative 3 over 2. Now that is a y-intercept, so if I wanted to, I could put it as 0 comma negative 3 over 2. That might make me feel a little more comfortable because the other one looks like a line. But so there's my y-intercept. My x-intercept is where y is 0. That's where this part is 0. And what would make this 0 if the top was 0? What are the things that are going to make the top 0? In here, we'd want negative 3, and here we want 3. Those are not things that will crash the function. They're things that make the top 0. And thus, oh, hold on. So if I take, I know what you're going to say. If I take a negative 3 and a positive 3, those 2 things will make my equation 0, kind of. Because the x-intercepts, I think places where it would hit, are at, where y is 0, negative 3 and negative, or at positive 3. But there's a big but. Who can catch what's wrong with this? There's several people. I'm going to start with you. If the hole's at negative 3, then you can't have an x-intercept in the same spot. So that one's disqualified. That cannot be one of your x-intercepts. Here's another way to say it. If you stick in negative 3, this equation's going to have a 0 on the bottom, and therefore it fails, and therefore it's not going to be an x-intercept there. Okay, that was pretty intense, but that's a review of rationals and how to find domains, vertical asymptotes, horizontal asymptotes, all those kinds of things about rational functions. Yes, sir?
So why isn't x can't be negative to vertical asymptote, not a whole?
Okay. Well, do you get that this has, there's a reason it's failing, and it's either because it's making an asymptote or a hole. Okay. We know the holes are only formed when you have something that's the same on the top as the bottom. That's why this one was a hole. And it's just defaults. If it's not a hole, then it's got to be a vertical asymptote. Did that answer your question? Okay. Okay, so that's one type of question. Here's another. These are about fraction functions, right? How is when I hunt for snipe, I usually get 3 per hour. Three snipe per hour. 1 second here. I brought somebody along with me. I don't know how good they're going to be. This is unknown snipe per hour. But together, we got 6. Oh, that'd be too easy. 4 snipe. This is important. In 30 minutes. Try to set up for me. Remember, it always comes down to a rate plus a rate equals a rate. see if we can set this guy up. A rate plus a rate equals a rate. And then make sure that you use the same units. And it should come out pretty easy. I'm giving you a simple one to start with here. I'm going to pause while you try that one. Okay, you should have said, if I can do 3 snipe per 1 hour, plus I don't know how much the other person can do per hour. I'm using n there. Then together, that's the rate plus the rate equals a rate, right? The together rate is 4 snipe, actually 8 snipe. Why am I doing this? For 1 hour. You get if you're going to do 4 in 30 minutes, you're going to do 8 in 1 hour. And that way you have the same units throughout the problem. And that's really important. And then you can just tell 3 plus what makes 8? And this one's not too tough to solve. It must be 5. Raise your hand if you had 5. Okay, good. Now those can be more complicated, but that's an example of the rate plus the rate equals the rate type of question. All right. In this problem is also where we met the box problem. Do you remember the problem where you cut the corner out, but you don't know how big you cut out? I encourage you to do one of those with me right now, just really quick. If this is x and 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 x, and this is 10 and this is 8, then its area would not be 10 times 8. It would be, I always start with a picture and then a pure form of the formula. Area equals length times width. And if they told me the area, I'd stick it right here. But let's say they didn't. Then the length would be not 10. But when you fold down these dotted lines here, you would have a length of smaller than 10, or 10 minus 2x. And then the width would be smaller than 8. It'd be 8 minus 2x. And then that's just getting it set up. And then since we don't have calculators in the test, we couldn't do one like where this equaled 400 unless the numbers come out really nice so you can get it all together on one side, factor it, set it equal to 0, and get the answers that way. If the numbers were nice enough, you could set this equal to 0 and solve. But all right, so that is the box problem. I think that's enough for this chapter. I'm going to pause for a second to make sure. Yeah, I just want to remind you that word problems is in this section, and therefore there will be some word problems. For my general advice in word problems is always set up a picture that is labeled very thoroughly, then always start with the pure form of the formula and stick things we know from the picture into the formula, and then you can solve it from there. A lot of times they're quadratics, so you get them all set, factored, and equal to 0, and then you, let's say it was as simple as this. You'd say x equals 3 and x equals 2, and then you found your answers by factoring. So basically, word problems in this section were one of the harder parts. Okay, that's all I got for you for that chapter.